Okay, welcome to your last lesson of the week. I am excited to be wrapping up today your lesson on simple machines. So I'm going to get into Schoology and kind of go through the same process that you have to go through. So I am going to open the PowerPoint, which I've already done actually here. So you click on the PowerPoint, and this is where I'm going to be taking notes from today. I'm going to go a little bit faster in this one because you guys are welcome to go back and actually look at the PowerPoint, but I'm going to give you some suggestions and tips for how to calculate these. So we're looking at 3 more simple machines. We've already done levers, okay, thinking about levers. That's where you have a fulcrum. And depending on where that fulcrum is, you either create a mechanical advantage less than 1 or greater than 1. You had a wheel and axle, and the wheel and axle, remember if you put the effort force on the axle, then you will have a mechanical advantage less than 1. If you have the effort force on the wheel part of it, driving the axle, then you'll have a mechanical advantage greater than 1. And then we had our pulley system. The pulley system has either a mechanical advantage of 1 or higher. That's why you would implement a pulley system. So now we're going to talk about the last 3 simple machines here. Let me go ahead and present it. Hopefully I won't be in the way too much here. I can make myself smaller. Oops, not sharing it. That's not what I meant to do. Let me close out, present. Here we go. So we have 3 different simple machines that we're actually going to be looking at now. We have the inclined plane, which we haven't talked too much about. You saw it on day 1, but the idea of an inclined plane, getting that roller coaster up to the top so that it can drop you. We use an inclined plane to do that because it takes less effort to get it up there. If I had it go straight up like this, it would take way too much effort for an engine to make that work. So that's the idea of an inclined plane. A wedge is going to drive, so you have your effort force like this, it's going to drive apart, let's say wood in this case, split apart wood. The effort, this will always have a mechanical advantage greater than 1 as well. So these ones always have mechanical advantages greater than 1. So does a screw. So we're going to talk about the idea of a screw. This right here is a car lift, showing that when you screw this up, then it's going to be able to lift a car, which is crazy to even think about. You can literally do it with this little tiny machine. So we'll talk about all of these and how they all provide mechanical advantages greater than 1. Let me click in here. So the idea of a ramp here, or in this case, we're going to call it, an inclined plane, okay? But the idea of a ramp, I'm going to actually go through these first couple because the first couple are just examining the idea of mechanical advantage, which we already know. But the mechanical advantage of this box right here, moving up the slope, is a 4 to 1. What it means when we say that this has a mechanical advantage of 4 to 1, it means it takes 4 times less effort to move this one than it would to just lift it straight up. But with that, we're going to find out that the distance is 4 times as long. So even though it takes us 4 times longer in distance, it's also making the effort that I have to put in 4 times less. So that's kind of the drawback of mechanical advantage. So the effort force is 4 times less than the magnitude of the resistance force. That's creating a mechanical advantage. For anything heavy, that's why you would create this idea of an inclined plane so that way it distributes the weight and it makes it easier. The distance traveled, though, is obviously a lot further. The effort force travels 4 times greater distance than the resistance force. Okay, so we've already talked about these, so I'm going to skip over this one, but that idea of a mechanical advantage greater than 1 is going to require less effort, and the mechanical advantage less than 1 is going to have greater effort that you need to put in. Mechanical advantage can never be less than or equal to 0. There's no such thing as that. So it's greater than 1, it's less than 1. There's no negative mechanical advantage. That's not a thing. We've already talked about this as well. So I'm a deer. This is recognizing that we take for the ideal mechanical advantage, we're using the distance, and it's distance of your effort over the distance of your resistance. And for your actual mechanical advantage, you're not taking distance, you're using forces. And again, that's the resistance force over the effort. It's the opposite of the other one. I'm a deer, AMA-free. Remember, those are my acronyms that I remember them from. Okay, an inclined plane is a flat surface set at an angle or incline with no moving parts. It's able to lift objects by pushing or pulling the load. Okay, pushing or pulling the load. So in this one, here is an image that we're going to look at. In this one, the way that we would calculate our IMA is by your distances, right? It's the distance of the effort over the distance of the resistance. Your effort is being applied here to this wagon. That's where your effort is. So the distance that you are traveling is actually this right here, 15 feet to get to the end here. Had I instead, the resistance, and what this is actually applying is like the resistance down, is actually this height right here to the top, which would be your 4 feet. So your IMA is going to be 15 over 4. 15 over 4, which will end up giving you 3.75. You could say 3.8 to 1 if you're putting that in the ratio of 3.8 to 1, which means that you've given yourself a mechanical advantage of 3.75 or 3.8. It means it would be 3.8 times harder to lift if you were just lifting that thing straight up. Okay, so now with the inclined plane, we're gonna see forces. So when you're given forces instead, then you know that you're gonna calculate your actual mechanical advantage, not your ideal. So AMA-free, your resistance force goes on top. So it looks like we have a resistance force of 50, and then our effort force is 20, okay? So I have to push 20 pounds of force, but I can therefore move 50 pounds of force. You can see that obviously we have a mechanical advantage greater than 1. So in this one, we end up with a AMA. When I take 50 over 20, I get an AMA of 2.5 to 1. Remember that the AMA is taking into account friction, so it's always going to be smaller than your IMA. The way that we figure out our percent efficiency is we take our actual mechanical advantage and divide by the ideal. We multiply by 100 only to get it to a percentage instead. And it looks like in this case, this is a 67% efficient. There's a lot of friction there. That's why it's not super efficient, because there's a lot of friction. There's 4 wheels on that thing. So there's gonna be a lot of friction, and also gravity is pushing it back towards you. So the actual mechanical advantage is a lot smaller than what we ideally would have. Okay. Talking about a wedge now. A wedge, the way I think of a wedge typically is like when you think of splitting wood, right? It's that concept of creating a wedge. Now, wedges definitely have a mechanical advantage greater than 1. So you have to think about what I'm moving here, what's moving, the force is here. My effort is going to be on the actual force where, let's say, the wedge hits the wood. Okay, that is going to be my effort force that I'm putting in, and I can split so much more. I create so much force coming out in 2 separate directions. I create so much more force coming out. That's how we can split wood. If I took my hand and I went like this with my hand, I'm probably not going to be able to create that gap or wedge inside a log. Well, I guess you see it in karate and such, but typically there's not going to be enough force behind that, where these axes provide that for us. So let's go ahead and see how we would calculate our IMA and our AMA for this one. Our IMA, our ideal mechanical advantage, we're going to have to talk about distances. This right here is the distance of the effort, okay? So when that wedge hits the wood, this right here is the effort distance, because that's the force that I'm applying. So that's going to be my, and it's perpendicular to the wood that you're hitting. That is going to be my effort. It's going to be 10 over the R, the resistance is the log, okay? So you're almost thinking of this. I know you're thinking of this as the top of the wedge, but that's not what it is. This is at the log. It's now split open 3 inches. It's split open 3 inches. That's the idea of this wedge, is that it's going to split open 3 inches. That is your resistance. That's where you find your resistance in this one. So this one is going to have an IMA of 10 over 3, which is going to be 3.3 to 1. And now let's talk about our AMA. We would need the forces here. So if I am able to put in 250 pounds of force, then the resultant force is actually going to be 700 pounds in either direction. Okay, that shows you that mechanical advantage there. So in this one, we always do our resistance force, which happens to be 700 pounds, over my effort force. Remember, they're switched, AMA free, over 250. I end up here with a 2.8 to 1 ratio, 2.8 to 1 ratio. Then we always calculate the percent of efficiency. We take our actual mechanical advantage divided by our ideal mechanical advantage, and we get the percent efficiency of this is about 84%. Okay, wedges are very efficient machines. Wedges tend to be very efficient. Okay, moving on to the last idea, and probably the most complicated. I actually have a bolt science article that is super useful and something that you're going to want to go back and look at. The formula sheet also has the idea of a screw, and it has the pitch and such that we're going to talk about. But really a screw is a combination of two different simple machines. It's like an inclined plane. So if you took that like idea of an inclined plane, it's wrapped around, you can see they're wrapping the inclined plane around like this, that screw. So they're creating that. But obviously we have torque with this one. And that's like the idea of a wheel and axle. So that's where screws were made. These always will have a mechanical advantage greater than 1. A lot of times way greater than 1. Screws tend to be very, very efficient. So let's kind of look at this. So the properties is for these are that they change rotary motion, they're used as thread fasteners, they have a very large mechanical advantage, but there's also a large amount of friction loss. So these have a lot of friction. If you've ever tried to screw into something that, like if you have a wall and you have a stud in the wall and you haven't gone into it and drilled a pilot hole, screwing into that is almost impossible sometimes. And it's because of that idea of friction. There's too much friction for you to be able to actually screw it. So please understand there is a lot of friction loss here. So the percent of efficiency a lot of times is not very high on these. Okay, so this right here is how we're going to read a bolt. And this is where I really want you guys to actually go in and read the bolt science article. So after you watch this, I would get in and take a couple notes on that so that you know where these different components are. One of the main things we're actually going to be looking at are, we're going to be given the numbers. This is the thread information. And what we care about is this idea of pitch. You're going to notice in our equation for IMA, we use the idea of a pitch right here. And what that means is when I go one rotation of this screw, when I screw it in one full rotation, I make a 360-degree turn with my wrench or whatever I'm screwing this on with. That is how far down the screw just moved. Okay, that's known as the pitch. Like it's gone one revolution, it's gone down into the wood by that much. And that right there is indicated here. The pitch is not 13, I will say. The pitch that we're going to care about is 1/13. 1/13. This is threads per inch. So what we're going to do, if there's 13 threads per inch, then the pitch is going to be 1/13 of an inch. 1/13 of an inch. So let me show you the formula. The IMA formula for a screw is still I'm a deer. Okay, I'm a deer. That's not going to ever change. That's for all the simple machines except for a pulley. On those, you count the strings. But on this one, I'm a deer. We take our distance effort and divide by our distance of resistance. Okay, so that's what we have going on here. What that means for this is that the IMA for a screw is going to be your circumference, which I don't know why this is happening, but its circumference equals 2 pi r, 2 times pi times r. The pi and the r are like in here somewhere, but it's 2 pi r. So we need the radius, right, of our effort. That's really important. It's not the radius of the screw because we have something like a wrench or something that we're actually moving this with. It's that radius. So the radius of the effort divided by the pitch. So here, our pitch is 20. which means, well, actually I should say our threads are 20 per inch. So our pitch is going to end up being 1/20. Let me fill in some of the information here. It says here, what is the IMA of a screw above if the effort is applied with an 8-inch long wrench? So you can kind of see the math that we've done here. We take 2 pi times our 8-inch, because that is our radius, okay? That's our screw radius for where I'm going to be applying force on that wrench. And then we divide by the pitch. We end up with this number right here. So you'll notice that in this class, we do a lot of converting. This right here is really close to 1,000. So we would be putting 1.0 times 10 to the 3rd power, which ends up being 1,000 as well. I'm okay if for now you guys leave this number, because we're probably going to be calculating AMA anyways and going from there. So in this one, we are going to calculate for the same scenario. Now I'm going to calculate my AMA, which means I need to give you guys my forces. So with 35 pounds of effort, okay, that's going to go down here. With 35 pounds of effort, I can actually create this force right here downward at 1,200 pounds. Again, screws are extremely high mechanical advantage. Okay, they are going to produce an extremely high mechanical advantage. What we're going to see is that the percent of efficiency is not going to be quite as high though, right? So on this one, we expected it to be 1,000 times better, 1,000 times more. If I had 1 pound of force, I should be able to go 1,000 pounds down. That was my ideal mechanical advantage. But in reality, with all the friction that happens with these, it ends up being, if I take the 1,200 divided by 35, it ends up being 35.29. So my 1,000 did not happen. It's not 1,000 times efficient. It's more like 34% efficient, right? 34 times more efficient. So what I have here, if you guys look at this, my percent of efficiency is only 3.4. It's very, very low efficiency, meaning I can't assume that if I use a wrench, I'm going to be able to turn it with 1,000 times more or less effort. It's really a lot less than that because of the friction that happens with screws. Okay, so that is all, and that's the idea of why is it so low, because you have a lot more force coming back at you too, right? That friction. This is just a quick reminder, and we did this yesterday, so I'm not going to go over it too much, but this is, if you think of a bike, you actually have a lot of stuff going on here with a bike. You have a wheel and axle, the idea of a wheel and axle, right? You're putting force on those pedals. That creates the wheel and axle. You have wheel and axle in here as well. This right here is a wheel and axle system. That's why you can create in a mountain bike. You can like flip over gears and it will create a mechanical advantage less than 1. Or you can like flip it back and have a mechanical advantage greater than 1 because you need to get up that hill, okay? So that's the idea of bike, when you're like tuning the bike thing, that's the idea of mechanical advantage as well. I love the idea of a bicycle. But the way that they function is on a pulley system as well. And so what you would do is you would actually take the mechanical advantages of all of them and multiply them together. We saw an example of that yesterday with a pulley and a lever at the same time. Those are a little bit less common than bikes, but it's that same concept of just multiplying those mechanical advantages together. And that is all for today. You do have some practice problems on this for tomorrow. So today you were just taking notes. Tomorrow you'll actually go through and do some practice problems with this. Good luck, and you are done with Module 1 after this. You'll turn in your work tomorrow. So tomorrow, turn in your whole week module, and you'll get your Module 2 assignments as well. That is all.